Hi guys, my intention this week is to finish taking a little bit of a look at this curve plotting that we started off last week and run through how you're going to do the SolidWorks modelling for the third task, and then I'm going to leave you to it to get that work done between now and the end of this semester. Okay, so the SolidWorks stuff, unless you've got access to the SolidWorks at work and the version and all the extras that are required to do the analysis, you're going to need to do that software stuff here. Okay. So last week I gave you some data in a table similar to what you've got in the assignment, and asked you to take a look at and plot that and have a think about what shape of curve might fit with that data. So I've done that on autograph on the screen. So what kind of curve would you suggest fits with that? There's really two that you could attempt to fit to that. Either a sine or a cosine. Which one would you think would be the best to choose there? Why would you say that? Because of where it starts. In what way, Mike? Okay, yeah. So what you're saying, if you plot a cosine with no phase shift, it starts at an amplitude of the maximum amplitude. The sine wave starts at minimum. And this one is starting high and going down. But the main thing is a cyclic. You could fit a sine wave to it just as well as you could fit a cosine wave. So if I enter the basic function for a cosine, what I'm trying to encourage here is that you don't just fiddle around with the parameters at a function until you make it fit. You take a mathematical approach to estimating what the amplitude, the phase shift, and the constant offset is. So if we enter the basic function, y is cosine we wanted, didn't we? Cos x. Bearing in mind, what you should bear in mind here is that autograph will assume your angles, or by default the angles are in radians. Okay, so we're working with the angle here in radians. So that's the basic cosine function, repeating around the x-axis with a amplitude of 1, a phase of 1, and a frequency of 1, and no phase shift. Okay, how can we approach? How would we try and approach? Just come out a bit, making the amplitude of our function close to what the amplitude of our data is. Sorry, Mike? Yeah, how are you coming about that figure? We got this is there to there is the amplitude of the function. Yeah. There to somewhere near halfway, or to halfway between top and bottom, is the amplitude of the data. What's the easiest way to get to the distance between halfway in the top or halfway in the bottom? the amplitude is that. How can I get that for any cosine function the most accurate way? Yeah, what we do is do the peak to peak value and half it. So if we take our highest data value, this one, and our lowest data value, that one, and half the distance between them, we've got the closest we're going to get to our amplitude. Yeah. So that your 1.6 or whatever you said it was might well be right, but I'm just kind of pointing out that that's the mathematical proof of that. So this bottom data value here, let's just get, I'm going to put all this. The amplitude is 1.37. We can add that to our function, like so. Now it looks a little bit closer in amplitude, this function, to what we've got with the data. The next thing to look at is to get it shifted up the y-axis, i.e. determine what the constant is on the end, the plus k on the end of the function, because the standard form is the amplitude times the cosine of x plus or minus a constant k, which is going to shift it up and down. How can we determine what that is? We've effectively got to shift this point up until it comes into the middle of that waveform. How can we do that? Yeah, that comes from, Mike, the amplitude plus the lowest value. Yeah, that's as close as we're going to get at this stage. These can always be tweaked afterwards, but we're trying to estimate them and get them as close as possible mathematically. So we're talking about 1.37 plus 0.16. So we're now shifted, and as you go through this process in your assignments, you can take screenshots of each stage to show how you're developing this towards the ultimate function to fit that data. Okay, and then perhaps make fine adjustments towards the end. So the next thing to consider then is the frequency. So that's going to be some multiple of x in here to get the frequency of this blue waveform to fit in with the frequency of that plot of data. So how can we approach frequency? What? To the same point. Yeah, we could do that if we had a complete cycle. We haven't got a complete cycle, have we? So what could we do? Could do a half cycle. Yeah. So between, sorry Mike, what did you say? If we aim for a half cycle, if we got a half cycle, full cycle would be between a peak and that same peak. A half cycle would be between that negative peak and that positive peak, wouldn't it? Yeah. Yeah, that would give you a whole cycle. Yeah. Yeah. So that'll give you how many seconds is a full cycle on this waveform. A half cycle, sorry. What would give you a half cycle on these waveforms? The first thing I want you to do with regard to this exercise is on the W drive on the network, the public drive, there's a folder with my name on it, and inside there's a folder called Advanced Maths Load and Exercise. That's got the necessary assembly models in you need to do this analysis. It's a read-only folder. You need to make a copy of that folder to your USB drives. Okay, so if you could just copy that folder into a USB drive or somewhere else that belongs to you is the first thing to do. And while you're doing, and on top of that, you can start up SolidWorks, which is in all programs, engineering, SolidWorks 2013. That takes a little while to start up, so do that, please. Well, next thing we need to do is get SolidWorks to load the simulation software, which is an add-in. Okay, so you go to this top box here. If you can just watch it through and then do it, please. Click add-ins, and then the add-in we want, we tick this box on the left here to load up SolidWorks simulation, and OK. If you get any dialog boxes up asking for acceptance, please say yes. Accept. Alright, everybody done that? Yep. So next thing to do is in the folder that you copied, if you what you've got in there is 3 parts, a web, a plate and a base, and then those have been turned into 3 different assemblies. I want you to load up the assembly with no webs. Right, people, just a couple of navigation around things with regard to SolidWorks. Are you all listening? If you double click the wheel, you fit the model to the screen. So if you've zoomed in, zoomed right out or anything, a double click on the wheel will get you back to there. If you click and hold the wheel and then move it around, you can rotate around the model and have a look around it. Okay? You go back to the normal trimetric view from this menu here and pick that one, and you're back where you started. Okay, because you're going to need, once you've done your analysis, you're going to need to look around the bracket to see where the hot spots are as far as stress and strain are concerned and so on. Okay, but you'll need also to get back to here. The adding the simulation in has put an extra tab up here that you wouldn't normally get when you start SolidWorks. So we've got a simulation tab. Okay, so everybody got to that stage where they've got that model up. Yeah? Okay, I'm going to go through how to do the full range of simulations that you need to do for the assignment, and then the assignment has you also looking at the effect of adding the different webs. So there's 2 extra models in there. One's got a web on one side, one's got a web on both sides, so you can go through an analysis of the effect of adding those webs to the results of the original plots. So I'm going to show you how to do go through one iteration and look at the different kind of plots you can get, and then I'm going to leave it to you to do the full analysis with all the other options. Okay. So first thing we want to do is go to the simulation tab, and then up on the left corner here there's a study. It says Study Advisor. If you click the downwards arrow and select New Study, you can give your studies names. I'm just going to leave this one as Study 1. Okay, for the has anybody not got that? Study 1, and there's a range of studies to choose down left here. We're just going to do what is effectively the default study. We're going to do a static study on this bracket. Okay, so as long as you've got Study 1 there and you've got static selected, you can tick the little green OK tick at the top of the dialog box. Okay. You now get a new navigation area here around the study that you're now doing. Alright, so we've got a range of things that we need to do to be able to set this study up before we can run it. The first one is we need to set some fixtures, or at least one fixture. So what we're going to do is rotate this round and say click the back face, right click fixtures and say fixed geometry. If you zoom in on there, if I zoom in, you notice I've got three. Notice that I've got 3 arrows. What that's saying is we're constraining that back surface in all 3 planes, which is what we want to do. It's like fixing that bracket to the wall, and it's not going to move on that back plane. So it's possible, if you're doing other different analyses, that you might allow it to move in 1 or more directions. So you might only fix it in 1 plane, you might fix it in 2. Here we're fixing it in all 3 planes. So there are options. There are other options we could use, but we don't need to do those. So we're just doing a standard fix in all 3 planes. Okay? And tick. Please select the reference. Hang on, I'm just going to do that again. Right click, select that, right click fixtures, fix geometry, and tick. Okay? So that has fixed our back plane so it's not going to move. Okay? So that's the first thing you need to do to set up an analysis. The second thing we need to do is set up external loads. We're going to put our load onto this top face of that bus. That's where the load's going to be applied. So you need to select that so it goes blue. And then right click external loads and select force. And you need the arrows to be pointing down onto that face. If they're pointing upwards, select reverse direction and the force would be the opposite way. So we want our force to be downwards onto that surface. Once you've done that, we want newtons, and I think the assignment says 15,000 newtons. Yeah, click OK. Okay. Everybody happy with that so far? You all done that, yeah? If you double click your wheel and so you can see your whole model, and then you're ready to go with the next bit. The next bit is we've got to actually set up what's called the mesh for the model. So if you right click mesh and select create mesh, okay, we can then decide how coarse or fine we're going to analyse. So we can set a coarse or fine mesh. For the benefit of this exercise, we're going to leave it with the default, which is a sort of mid-position mesh for this bracket. So just simply click the tick, and then that will go through the process of meshing, and that will put lots of triangles all over your bracket showing the mesh. It's actually dividing the whole model up into small parts, so it can do the maths on each part and then come up with an overall answer. Alright? So if you change that mesh value to coarse, the triangles will be bigger. If you change it to fine, they'll be smaller. Obviously, well, not obviously, but the finer mesh you have, the longer it'll take to calculate your final answer when you do your analysis, which is probably not too much of an issue with this bracket, but if you had a much more complex simulation to do, it would do. Okay. There's some, not this add-in, there's another add-in called SolidWorks Flow Simulation. And on the renewables module at level 6 at one time, they were doing some flow rates around aerofoils, and those simulations were taking over an hour to calculate. So you need to be careful in considering, probably best to try a coarse mesh to start with, and then see if you need to modify it. And there are other range of things you can do. So in areas of particular interest, you can set the mesh finer around weak points in the model as well if you want to. But we're not interested in doing that. Okay. So once you've set up your mesh, as that on the screen now, you're then ready to run the analysis on that bracket. Okay. So what we need to do now is go up here and click Run. Material is not defined. Did I tell you what material to make it? Right. No worries. I'm going to show you, hang on. I can't remember about myself now. Where's that? That will be, yeah. Apply material. Just pick the default alloy steel. That'll be fine. And apply. Apply and close, and then click run. We then get the analysis taking place. So it says solvent. Are you listening? Because we'll not get through this, and I really want to get through all of this in this session. I can leave you to it. Okay? What you get from that, by default, is you get a stress plot, like the one here. The coloured bars, the different colours show you the differences in stress around that bracket. So the red part is where the most stress is, and it indicates what the stress is in newtons per metre squared. Okay, so the red areas are the areas of high stress, blue areas of low stress, and then the other colours, the bits in between. You also get a displacement plot, which shows you in millimetres the picture exaggerates the displacement so that you can clearly see the direction of it. Okay, but we're talking about a 2.346 millimetre displacement at the end here where it's red. And then these are, this e to the minus 001 is e to the power of 001. So it's times 10 to the power of, so they're small, much smaller numbers. Okay, and then the last one is a strain plot. And again, the red areas are where the most strain are. Okay, for the assignment, what I want you to add to that is an investigation. I've asked you to investigate also into factor of safety. Okay, so there's two different factor of safety things that you can look at, and what you need to do those is if you right click results and select define a factor of safety plot. So if you get to that bit, please right click results and select define factor of safety plot. With this dialog box area over here, if you see some arrows up the top here, it means that dialog box has got more than one page to it. On this factor of safety plot, you're going to leave everything on the first page. You're going to leave the multiplication factor for all of it on 1. There's two plots you can do here. The first one we're going to look at is the factor of safety distribution. So just leave that as default and tick. Okay, now what that's telling you is the red areas have a factor of safety of 1.82, going up to any blue areas, which I can't see any, having a factor of safety of 206,791.27. Okay, so we've got a lot of red factor of safety stuff here. Okay, and the assignment is asking you to look at areas that are above a factor of safety of 5. So what we need to do that is right click results again define another factor of safety plot. This time go to the last page and tick the little box that says areas below a factor of safety, and then put the number 5 in the box underneath. So that first factor of safety plot showed us what our minimum factor of safety was currently on this bracket. When we tick this one, what we get is a plot that shows us in red anything over 5, anything under 5, and blue is where the factor of safety is over 5. So we've got significant areas in this area, this plate of this bracket, that are beyond the factor of safety of 5, which is what we're looking for. Okay, so they're the key plots that I'm asking you to discuss and show for the different options with this bracket in your assignment. Displacement plot, stress plot, strain plot, factor of safety distribution, and then the key one is to investigate the whether you can make this have a factor of safety of 5. Okay, so in doing that, you're going to need to investigate the other 2 models in the folder, which is the assembly with assembly with a bottom web. I just open that up, it's got a web on the bottom, and then the other one's got a second web on the top here. Okay, if you can find enough words, you might like to investigate other options if you know what you're doing, but I think that will give you enough to do in terms of words you got for your assignment. Is everybody happy with that and being able to do that analysis?
So this area is 3 columns.
Yeah. All right. Okay. Yeah, the other ones show you different colours, didn't they? This one is, the last one is just showing you what is within your factor of safety that you set, 5, and what is outside it. So if we were trying to design this bracket and the specification was that it would take 15,000 newtons with a factor of safety of 5, this is analysis we could do to prove, to design, help us design and prove that would withstand that factor of safety. All right? Yeah? Agreed? Yeah, I'll come over there and show you, Dan.